Hello friends, welcome back to tutorials. Our next topic is Myhill Nerode Theorem. It states that if the definition of the language L divides all strings into finite number of classes, then the language L is a regular language. For example, if L is a set of all strings which ends with 0. Now this definition divides all strings into two classes. Strings which doesn't ends with 0, and second class is strings which ends with 0. If a language divides all strings into n classes, right? Then the finite automata which will accept this language will have n states, each state corresponding to each class of a string. It would be more clear after this example. Let L be a language. It is a set of those strings which have even number of zeros and odd number of ones. Now this definition of language has divided all strings of 0 and 1 into 4 classes. Right? Let it be A, B, C and D classes. Then class A corresponds to those strings which have odd number of 0 and odd number of 1. Class B will correspond to those strings which have even number of 0 and even number of 1, and class C will correspond to those strings which have odd number of 0, even number of 1, and class D will correspond to those strings which have even number of 0 and odd number of 1. Now we have to construct a finite automata which will accept the language L. Since the language has divided all strings of 0 and 1 into 4 classes, the finite automata which will accept this language must have at least 4 states, each corresponding to each class of strings 0 and 1. Right? Since there are 4 classes, there will be 4 states. Now, state A corresponds to class A, state B corresponds to class B, state C corresponds to class C, and state D corresponds to class D. Now when we apply any string of class A, the machine will jump from its initial state to state A, and when we apply any string of class B, then machine will jump from its initial state to state B, and when we apply any string of class C, the machine will jump from its initial state to state C, and when we apply any string which belongs to class D, then machine will jump from its initial state to state D. Now when we apply any string which has even number of 0 and even number of 1, then machine will be in state B. Now we have to find out its transition. Here the machine has read, when the machine is in state B, it has already read a string which has even number of zeros and even number of 1. When it reads 0, then number of zeros in the string which has read will become odd, right? Then it will go to state C, which corresponds to the class of strings which have odd number of zeros and even number of 1. And when it reads 1, then number of ones will become odd and number of zeros will remain even. So it should jump to state D, which corresponds to the class of those strings which have even number of zeros and odd number of 1. even number of zeros and odd number of ones. Here it is odd number of zeros and even number of ones. Now we have to find the transition of state C. When the machine is in state C, it means we have applied a string which has odd number of zeros and even number of 1. When we apply 0 here, when the machine is in state C, then the number of zeros will become even, right? And number of ones will remain even. So it should go to the state which corresponds to even number of 0 and even number of 1. So when you apply 0, it will jump to state B. Similarly, in state D, when we apply 1, right? When we apply 1, then the number of ones in the string which the machine has been read will become even, and number of zeros will also be even. So when we apply 1, it will jump to the state which corresponds to even number of zeros and even number of ones. Now let us find its transition for input symbol 1. When we apply 1, it would be odd number of zeros and odd number of 1, right? So it will jump to state which corresponds to odd number of zeros and odd number of 1, that is state A. Right. Now let's find the transition of state D for input symbol 1. Here the machine has already processed a string which has even number of zeros and odd number of 1. When we apply 1, right, then number of ones will become even and the number of zeros will remain even. So it will jump to state B. Now we have to find its transition for input symbol 0. When we apply 0, the number of zeros in the string which machine has processed will become odd, right? And number of ones will remain odd. So it should jump to state A, which corresponds to odd number of zeros and odd number of 1. Now let us find the transition of state A. State A corresponds to odd number of zeros and odd number of 1. When will we apply 0? Right? Then a string will have even number of zeros and odd number of ones. And when we apply 1, then the number of 1 in a string will become even and number of zeros will remain odd. So it should jump on state C. Right. Now the finite automata should accept only those languages which have even number of zeros and odd number of ones. Now the state corresponds to that language is D. So we will make it final state, because when we apply any string of even number of 0 and odd number of 1 to machine, it will jump to state D. Now we have to make its final state. When we don't apply any string, that is when the input is 0 number of 0 and 0 number of 1, right? Then where machine should be? Now here we have considered 0 is an even number. If a machine has read 0 number of zeros and 0 number of ones, right? It means the machine has processed a string of even number of zeros and even number of ones. So we have made state B, which corresponds to even number of 0 and even number of 1, the initial state of this finite automata. Why? Because when we don't apply any string, right, machine will remain in state B, right, which corresponds to even number of 0 and even number of 1. Because 0 number of zeros and 0 number of 1, right, means we have not applied anything, will be considered as a string of even number of zeros and even number of ones. Thank you very much.